Okie dokie. So I need to remember to not say okie dokie as best I can, because I've noticed I've started doing that quite a lot. Right, so in the last session, we started to design this experiment for bacterial media with like a few different ingredients. And we used this Python package called DexPy to design a fractional factorial experiment. So like the same amount of information as we would from like every combination, ideally, but with fewer experiments. So it spits out this pandas data frame of the design where it's got high and low values for each of your conditions. So then after that, it was up to us to replace each of the column headers with the appropriate name and the low and high value for each one. And I think that's about where we left it off. So this would have been a perfect time for me to put in an exercise if I had been more prepared. How do you guys feel about doing this as an exercise now, despite this cell being open? I guess you can hide cells, I know. But I don't know how to do that. Okay, never mind. Okay, well, I'll just explain through what I did. So I looped through this EXPD data frame in a list comprehension. I've split it onto 2 lines to make it a little bit more readable. And I'm looping through the columns of that, and then also the keys of this dictionary levels. And for each iteration, I am taking that column and using the pandas built-in replace function, which takes a dictionary, and I can say replace -1 with levels J low. So levels J in each case will be the dictionary key, and then it will replace -1s with the low, so 0 in a lot of cases, and 1s with highs. And then I reset the names of the columns to match. I'm going to open this notebook in playground mode, which is a mode where it's like changes that you make don't actually save. There we go. Just to avoid messing it up for you guys. So then yesterday I started to actually make all of these buffers, or the day before yesterday I did. Made a pretty bloated, probably overcomplicated function to calculate the weights and volumes of this, that, and the other for all of the buffers. But I ended up making them, and I have a picture somewhere, but maybe I'll put it in for next time. And then the problem I had was I wanted to randomize the experiments by, or randomize the wells that each of the 8 buffers will be in, because I was thinking, well, it's no good if we put, say, all of the buffer 0 in one column by the edge, because then if there is like a position effect in the plate, like for example, if they grow differently towards the edge, then that's the whole run sort of growing differently. So yeah, I wrote these few cells to try and randomize it. So I used a short list comprehension again with a F string. Zoomed in too much. To generate all of the well names. So this list comprehension uses a double loop which is something that you can do. Check the Python notes for professional section on list comprehensions for more info on that. But essentially, I've generated all of the 96 different well names. And then I downloaded, well, I'll explain what this download link is in a second. So I built another function that sort of creates the random well assignments where each column is each different buffer. And within that, these are the wells where the buffer is, or sorry, the media is actually in that well. And because it's generated randomly each time, I was like, I want to have it saved so that I can, only do it once. And yeah, I was worried that if I accidentally ran this cell again, then it will just regenerate and I won't be able to recover the actual layouts that I was doing. So these are the layouts that I've pipetted out into the plate. I did it by hand, which took maybe about 20 minutes. But as far as I know, I didn't make any mistakes. But we'll see. This cell, I think I was just making in some dead time just to try and show the different positions of the different buffer types. But anyway, here is, oh God. So this is the cell where I'm supposed to okay, I can tell you what I've done here. So yeah. Okay, so this command downloads the data from the experiment, which is stored up here. So the link that I'm copying is this link to the raw version of the file. Here we go. Okay, well, that's the well assignments. This is the actual data. So that's the link there that copies down to this computer. And when I plot everything, it's a mess. And again, like last time, we have that sort of initial dip in OD, which I want to try and mitigate for. So later on, I'm thinking I'm just going to cut it down the middle and just go from there. So one of the problems I had was that in this data frame, which I called screen, the well IDs are A03, A04, A05, and so on. So that's what this cell tries to mitigate. But don't look at that cell, because in absence of me having actually set any proper exercises for this week, I was pretty rushed. For the next couple minutes, I think an exercise could be to write a function like I have done down here, which reformats the well numbers so that there isn't one of these leading zeros in front of the single digit numbers, so that it can match our wells, which are formatted like this, no leading zeros. I'm going to set 3 minutes to do that. Send a message to the chat if you have any questions. Or want a slightly clearer explanation. It's lunchtime here, so it's sort of moving around all of a sudden. Oh no, you know what I've done? I've exited out of the tab with my timer. Oh no. Okay, that's no problem. Well, it was probably just about done anyway, so I'll go through how I've done it here. I'm going to delete all this just so I can go through it and explain it line by line. Okay, let me get up the screen.index. Okay, so the aim is to iterate through this and remove the leading zeros. And when I first started writing this, I was thinking, oh, I could use regex to extract numerical and non-numerical characters. But what I think I'm going to do instead is just locate it by position. So the first letter is always, or the first character is always the letter, and the second two are always the numbers. So I'm thinking the easiest thing to do is just to slice them out by indexing. So if this function takes in each one of these strings as ID, then the letter is equal to ID 0, then the number is equal to ID 1 onwards. So that will return it as a string. So we want to have it turned into an integer. Let's have it print the number and just run it as a practice. So it prints it out as a number, and when we turn it to an integer, it automatically, or the interpreter automatically gets rid of the leading 0. So that's pretty handy. Now what we need to do is stitch these two back together. So we can return letter plus, we need to turn this number back into a string if it's gonna be able to be added to the number, sorry, the letter. So in this list comprehension below, we're doing this function on every item in the index of the screen. So the new index is hopefully equal to Wells. Cool. Okay, so now it's formatted the same. That's good. Although now that I think about it, probably even simpler thing to do would have just replaced the index of the screen with this Wells object, given that they're going to be the same anyway. Oh well. Okay, so in this cell down here, I set the index of the screen to the new index that we just calculated. What am I looking at here? Well assignments. So well assignments is this data frame that I've made up here, right? And each of the columns are the different medias, and then within that there's the wells in which I've actually put those medias. And I'm trying to look at one individual column. So as far as I remember, I think recipe number 0 was pretty much just water. So I'm not expecting great results for this one. But anyway, these are all the wells that match up to well assignment 0. So in this cell below, I've gone for making subplots again, like I think we might have done in an earlier tutorial. And I'm looping through the columns of well assignments, because by default, when you loop through a data frame, you loop through its columns. And then I'm also looping through this array of subplot objects, which I've flattened out first to make it easier to iterate through. Then I create a group in each iteration, which is matching up these well assignments to the screening data that we actually got from the plate reader. And then I loop through the index of that subgroup. Let's see what one of these group looks like. There's probably still a variable saved as group, isn't there? So that will look something like this. And within each iteration of the loop, I make another loop that plots all of the columns. Sorry, it plots the time points, the absorbance long time points for that particular well. Then I'm setting title here. Just a second ago, I had these within the second loop, which was pointless. I should have had them one loop outside, and it removes the need to do it 10 times as many times or 12 times as many times. Okay, so as expected, the water-based recipe shows pretty much no growth. And some of these other ones do seem to show some. I think really I should have run the experiment for longer, but in the meantime, we'll just work with what we have. Okie dokie. I said it. So this is the point where I thought I could do with some advice from you guys. So what happened was I noticed that, again, there's this sort of dip in absorbance up until about 300 minutes, and then it starts to rise. So I was thinking, oh, if I just start the count at about 300 minutes and just cut off everything before that, then maybe it'll fit a little bit better. So I gave that a go. So I've got this new variable called screen trimmed. That's from 300 minutes onwards. And by way of sort of zeroing it, I subtracted the 0 minutes absorbance from all other absorbances in that trace. So yeah, just to bring it down to 0, I suppose. And then I try and adjust the names of the columns so that they all start from 0, if that makes sense, rather than just starting from 300. Instead, now it just starts from 0. Okay, once again, I've set some new bounds for the curve fitting, which I think I need to do some tinkering with, really, if I'm going to make it work for all of them. And then I start making a lot of subplots with 24 rows, 4 columns, and a fairly large figure size. And I've got this dictionary to catch all of the output. So within this loop, I go through the index of the trim screen, so that's the well numbers, and one of these figure objects. I fit a curve using the SciPy curve fit with one of the Gompertz equations, and calculate some parameters for W and T and K. I try and calculate the R squared here. So you'll notice at the top that from SciPy I import the Pearson R squared, and I run that on this variable ypred, which is the predicted OD at each time point according to the model that we've made. So according to the Gompertz curve with the parameters that we calculated through the curve fit. So the R squared value will measure the difference at each time point between the actual data the screen trimmed, and the predicted data widebread. And then at that point, it adds all of the data that we've calculated to this dictionary up here, output. And then we do some plotting. We plot the real data and then the idealized data with widebread. So this is what it looks like. And it looks pretty poor in terms of curve fit for a lot of them. So I'm inclined to think that one reason is not running the experiment for long enough. Like, we haven't actually seen the growth rate of these things plateau, really. Also, there's that initial dip I still can't explain. So if anyone has any ideas of what might be causing that, then yeah, let me know, and maybe we can try and solve that bug next time. So what I would have showed you after this, had the results been more sensible, would be then fitting a model to the sort of the average growth rate for each of the buffers. And then we can use the fit model to try and decide which of these parameters, which of the ingredients in the recipe is actually important. And I've written some code to do that, but I think if we go through it, I think we should bear in mind that the results, or at least the curve fit, is pretty questionable. So you'll notice that some of the R-squared values are okay. Like, for example, at H10 down here, the R-squared is 0.98, and considering it's out of 1, that doesn't seem too bad. But then when you look at the curve that we've generated compared to the actual, you get an idea of how 0.98 seems all right, but it's definitely lacking in some areas. Okay, so from the dictionary output that we made in the last loop, I made this data frame called screening results. The capital T at the end is a transpose method, so essentially it just turns it sideways. Yeah, see that? So we have each well, and for each well, the calculated maximum asymptote, the inflection point, and the growth rate. And for some reason, it's the same for every single one. So that's another problem, another bug that we'll need to try and solve in a bit, I suppose. Now, what am I trying to do here? So what I think I'm trying to do is loop through each of the well assignments. So the well assignments, we might remember, was a data frame. And as we loop through it, we'll be looping through the columns, the column names, 0, 1, 2, etc., which is also what I've been naming my buffers. So we can use that name to find the column assigned wells. So the assigned wells would be pretty much well assignments 0, say. So that's the sort of object that we'll get. And then we can locate from the screening results those wells. So let's give it a go now. Screening results dot locate, and we want the rows with those wells. So that's the first argument, and then the second argument is going to be a colon, which is just going to be all of them. So this is what's being produced in each loop, and then it's getting added to this dictionary results summary, which is how I'm storing the data frames in the meantime. And then I've got another loop, which goes through each of the objects in results summary and takes takes the mean of the growth rate, which considered that they're all the same every single time, annoyingly, the mean is going to be 0.025 every time as well. So the place where we'd ideally be at the end of this experiment is we've got our growth rates, or our mean growth rates for each buffer, each media, and we have the recipes of each media. So these are the inputs to our experiment, and this is the output. And the only thing left to do now would be to fit a model between the inputs and the outputs. And then we can use the model parameters to try and find out which of the ingredients are actually important. In absence of some sensible data, we can have a go at trying it anyway. So the model I was thinking of choosing was something called a Perceptron, which, as far as I can tell, is just a multiple linear regression. Is that right, Steve? But it's a binary classifier.
Which
So what I'd like here is a multiple linear regression. Do you know if scikit-learn has multiple linear regression?
I would expect it to have.
Okay, let's give that a go. Okay, so it looks like the scikit-learn linear regression is multiple.
Yeah, it
should we give it a go?
Yeah, it should be.
Cool, let's try it. So this might be the first time I've done scikit-learn in Python Club, but for reference, scikit-learn is a really useful data analysis model building library, which we'll look at more in the future. Pilcrow. Okay, so what have I done here? I've imported the linear regression from the scikit-learn linear model library, and I've created one of these linear regression objects. I've called it MLR, short for multiple linear regression. And when we look at the docstring of it, we can look at its parameters, which we initialize it with. So that will be talking about how to initialize it here. So we can actually initialize it with fit, intercept, and so on. I guess that means the C of y equals mx plus c. So the y-intercept, you can decide whether or not to actually use that. And it also has an example of how to use it at the bottom. So it's typically run with this .fit method, which is what I've gone for here. MLR.fit media recipes and list growth rates. So what happens in that model fitting process? Well, the parameters of the multiple linear regression model are adjusted over the course of iterations so that for each of these x values going in, whatever these get multiplied by is adjusted in each step, and then to minimize the error of the model according to the difference between the predictions and these growth rates. So the two things to do from here would be to, number one, try and evaluate the accuracy of the model, and then number 2 to try and find the size of each of the parameters, and use that as a proxy to find out which one of these parameters is actually the most important. If the model has like a parameter for 0 for, say, salt, then the chances are that it's not really incorporating that into its evaluation. Another thing that we should have done before fitting this model is scaled each of these between 0 and 1 or 1 and -1. But we don't need to do that because we have this data frame where it's already been done for us. So I'm going to have it fit to that, and then we're going to print ml dot get params. Sure. So one way to analyze the accuracy of the model would be to look at the R-squared score. So we already had a Pearson R-squared score. Here we go. That we took in earlier, and that takes in the true predictions versus, or sorry, the true values versus the predictions. So we're going to make this object called ypred, just like we did earlier, and it's going to be mlr.predict, and then xd. And then the Pearson R-squared score is going to be between.
I need a rest before I do the next door.
Yeah, all right.
Growth rates.
There's still some paint in the tray, so if you want to do it.
What have I done? Okay, so short of just tinkering for the rest of the lesson, I think I'm gonna wind it down there. Otherwise, yeah, it's just gonna be watching me tinker, which is gonna be no fun for anyone. So to quickly summarize what we've been over today, and apologies for not having many exercises this time. We used some assignments, or sorry, some media recipes that we worked out last time. So something like this. We looked at some randomization methods to randomize them within a plate, and used the functions that we had written earlier to process the data, or in this case, at least I'm using the ones from the answer sheet, but yeah, you get the idea. We did some well matching to make sure that we can match up each well with our experiment design. And then I had a pretty hard time trying to make these curves fit, which is a bit of a bummer. Yeah, does anyone have any ideas on the curve fit here? So the things that I was tweaking was the cutoff, so where I cut off the data to start looking at it, and the experimental bounds for each of these parameters. So in these tuples, that's the WM low, WM high, TM low, TM high, and so on.
I think you're right in that I don't think you've taken the experiment far enough.
No, I think I might need to repeat it. I think.
And I'm not that dip at the beginning. I'm not sure what that is all about. Could your cells be dying off when you introduce them to the media?
Yeah, it's strange, isn't it? So this happened last time as well. Yeah, quite a lot of them sort of dipped down. But then if we look at the old experiment from the pilot run, so this was just with LB. Okay, well, it's not as bad in this one, but yeah, there's still a slight dip. Where are we?
Or are the yeast cells clumping or something like that and causing the optical density to change?
Yeah, I don't know. It's hard to say. So whatever it is, it's happening in both.
Yeah.
Maybe it's a mixing thing where so the way I was adding the cells was I made like a small starter culture on the day of the experiment. So a sort of little 5 mil in LB culture that I grew for a couple of hours, and then I multi-channel pipetted about 10 microliters of that into each one of the wells. And maybe what it is that in the first couple of readings, maybe there's some sort of mixing problem, which is sort of resolved by about 50 minutes in, or whenever this is. What do you reckon?
I don't know. Could they actually
either way, I should definitely.
Could they actually be separating the cells? Can the cells be sort of floating to the surface or something like that? Very weird.
Yeah, maybe. I don't suppose it could be condensation or anything, right? Like
oh, shouldn't.
So if the whole growth chamber is the same temperature, nothing should condense on the lid, right?
No, it shouldn't. It should be all right.
Strange. Okay, so I think what I'll do is I'll repeat today's experiment next week, or next time we have the chance. So in the next session, what we would have done is used the information from our model about which parameters are and aren't important to then design the next round of experiments, which focuses in much more detail on far fewer of those parameters. But in absence of proper data and a proper model, that's not quite possible. So I'll think of something. Yeah, leave it with me. Yeah, we'll get there. All right then. Okay, so I guess I'll stop recording around about there, and I'll see you all next